Concepts from biology, particularly the idea of emergentism, provide a fascinating lens through which to explore the origin of the universe. Emergentism refers to the process by which complex systems and patterns emerge from the interaction of simpler components. This principle can shed light on our understanding of how the universe evolved from an incredibly dense and homogeneous state to the vast and complex cosmos we observe today. In the context of cosmology, the early universe is often described as being in a state of high energy and homogeneity. As the universe expanded and cooled, small fluctuations occurred at quantum levels, resulting in tiny changes in density. These tiny differences can be compared to the components of a biological system, where the interaction of individual components leads to the emergence of larger, more holistic structures. The concept of emergence helps explain how such tiny fluctuations eventually led to the formation of galaxies, stars, and planetary systems, demonstrating the transition from simplicity to complexity over time. In addition, understanding emergence in biology can help in the study of self-organization in the universe. Just as biological systems such as flocks of birds or cellular structures can create complex patterns without central control, the universe exhibits self-organizing behavior at cosmic scales. Gravitational interactions between matter can lead to the formation of large structures, such as galaxies and galaxy clusters, out of primordial chaos. This process emphasizes how fundamental forces and simple interactions can give rise to complex structures and systems in both biology and cosmology. In addition, concepts of emergence in biology raise intriguing questions about the nature of life itself and its place in the universe. If we consider the universe as a complex system, the emergence of life can be seen as one of its many outcomes. The study of complex adaptive systems in biology, including ecosystems and evolutionary processes, can provide insights into how the emergence of life reflects basic physical laws and cosmic dynamics. Moreover, interdisciplinary approaches that combine insights from biology, physics, and philosophy can expand our understanding of both the origin of the universe and the emergence of consciousness. By studying how individual and collective behavior emerges in different contexts, scientists will be able to better understand how conscious beings are connected to the cosmos, and how the universe itself may contain forms of information processing or consciousness at different scales. Concepts of the emergence of life in biology enrich our understanding of the origin of the universe by emphasizing the complex interplay of fundamental processes that lead to the formation of complex structures and systems. This view promotes a more integrated view of the cosmos and life's place in it, encouraging research that spans across disciplines to deepen our understanding of being. Neuroscience can provide significant insight into our ability to comprehend abstract concepts such as nothingness and the early universe by studying how the brain processes complex ideas, shapes understanding, and interprets experience. While people are trying to make sense of these deep philosophical and scientific concepts, neuroscience offers explanations for the cognitive mechanisms involved. One key aspect of this research is how the brain conceptualizes the idea of nothingness, a concept that challenges our traditional understanding of existence. Neuroscientific research shows that the human brain does not tend to comprehend the absence of something. Instead, we tend to fill in the gaps with context-rich interpretations based on sensory experience. This tendency is rooted in our evolutionary need to navigate the physical world that shapes our perceptions and cognitive frameworks. The brain's dependence on context means that thinking about the concept of non-existence often leads to abstract thinking, which can cause feelings of uncertainty or discomfort. In addition, understanding the neural basis of abstract thinking may shed light on how humans imagine the early universe, which encompasses vast scales of time and space, as well as conditions that seem completely alien to human experience. Neuroscience has identified brain regions involved in reasoning, imagination, and spatial cognition, such as the prefrontal cortex and parietal lobes. These areas are engaged when people try to build mental models of cosmic phenomena or visualize timescales beyond everyday experience. The brain's ability to create and manipulate abstract representations allows us to formulate hypotheses and ideas about the origin of the universe, even if these concepts remain beyond direct observation. Furthermore, the concept of cognitive elasticity plays a key role in how we adapt our understanding of complex topics such as the early universe. Neuroplasticity, the brain's ability to reorganize itself in response to learning and experience, makes it easier to incorporate new scientific knowledge into existing mental frameworks. As our knowledge of physics and cosmology expands, humans may change their view of the universe and its initial conditions. As a result, people attempt to construct mental models of cosmic phenomena or visualize timescales beyond everyday experience. In addition, exploring the philosophical aspects of neuroscience can shed light on how concepts of nothingness and the origin of the universe intersect with existential questions about consciousness, perception, and reality. This research can lead to deeper insights into the human condition and existential experience, further enriching the debate on the nature of existence and non-existence. Neuroscience offers valuable insights into our ability to comprehend nothingness and the early universe by studying how the brain processes abstract concepts, builds mental models, and adapts to new knowledge. This understanding links cognitive science to philosophical inquiry and provides a framework for exploring the nature of existence, ultimately increasing our appreciation of the deep mysteries of the cosmos. Psychological concepts of perception can significantly influence our theories about states before the Big Bang, shaping how we interpret and conceptualize the origin of the universe. Perception, which underlies human cognition, not only dictates how we perceive reality, but also influences the framework we use to understand abstract concepts that lie beyond direct observation, such as conditions before the Big Bang. One key psychological aspect is that human perception is limited to sensory experience. Our brains evolved to interpret information based on direct physical encounters and relationships in a three-dimensional world. When theorizing about the state before the Big Bang, which may involve measurements or conditions beyond our sensory limitations, scientists must rely on abstract reasoning and analogies. This dependence may affect the formulation of theories about the early universe as complex phenomena are described in more comprehensible terms, potentially leading to interpretations closer to our perceptual experience rather than strictly conforming to scientific rigor. In addition, cognitive biases determine how scientists treat abstract cosmological concepts. For example, the human tendency to think teleologically can affect our interpretations of the state before the Big Bang. This bias can lead us to attribute purpose or direction to the formation of the universe, which may not reflect underlying physical principles. Such biases can shape theoretical narratives and influence the acceptance of certain models over others, thereby influencing the direction of research and inquiry in cosmology. Moreover, our understanding of ambiguity and uncertainty from a psychological perspective plays a crucial role in interpreting theories that predate the Big Bang. Human cognition often struggles with ambiguity, which leads to attempts to create order out of chaotic or uncertain concepts. In the context of the early universe, where initial conditions may be poorly understood or radically different from our everyday experience, this tendency can lead to a penchant for deterministic models that promise clarity. Advances in theoretical physics require balancing this desire for understanding with the uncertainty inherent in such complex concepts. In addition, psychological perceptions can also influence the collaborative nature of scientific research. How theories about the pre-Big Bang state are communicated and understood in the scientific community can affect the collaboration and synthesis of ideas. The influence of group dynamics, social approval, and consensus can lead to the normalization of certain theories and the marginalization of alternative viewpoints. This dynamic is crucial because it shapes the research landscape and influences which theories take the lead. Psychological conceptions of perception significantly influence theories about pre-Big Bang states, shaping our interpretations of complex and abstract phenomena. The limitations of human cognition, cognitive biases, reactions to uncertainty, and collaborative dynamics all contribute to the framework through which we understand the origin of the universe and ultimately influence the focus of research in cosmology. Parallels between cosmic and biological evolution reveal surprising similarities in the processes that govern the development of complexity in both the universe and life on Earth. By examining these common characteristics, we can further understand how complex structures emerge in very different contexts. One of the most striking parallels is the idea of gradual change through incremental steps. In cosmic evolution, the universe began with the Big Bang and has since expanded, cooled, and evolved through various stages, from the formation of subatomic particles to the creation of stars, galaxies, and eventually complex structures such as planetary systems. Similarly, biological evolution occurs through the gradual change of species over time under the influence of genetic mutations and natural selection. Both processes illustrate the path from simple beginnings to increasingly complex forms, emphasizing that complexity can emerge incrementally from simpler components. Another significant parallel is the role of randomness and chaos in both cosmic and biological contexts. In the universe, quantum fluctuations in the early universe can affect the distribution of matter, leading to the formation of large-scale structures and determining the paths of cosmic evolution. In biology, genetic mutations occur randomly and can create variations among organisms, some of which may confer advantages under certain conditions. In both scenarios, randomness introduces variability, and underlying laws, such as gravity in cosmology and natural selection in biology, help guide the trajectory of evolution toward more organized states. Moreover, both cosmic and biological evolution involve processes of self-organization. In space, gravitational forces lead to the self-organization of stars and galaxies as matter coalesces under gravity to form complex structures. In biology, self-organization is evident in the development of complex multicellular organisms from simpler cellular aggregates, where individual cells combine to form tissues and systems through concerted interactions. Both systems demonstrate how interactions between simpler components can lead to emergent properties that cannot be predicted based on components alone. In addition, both fields demonstrate the concept of interdependence and interconnectedness. In the universe, galaxies interact gravitationally to influence each other's evolution, and stars, through nuclear fusion, produce elements that become the building blocks for planets and eventually life itself. Similarly, in biological ecosystems, species coexist, compete, and cooperate to shape each other's evolutionary pathways. This interconnection emphasizes the importance of relationships and interactions in the development of complexity, both in space and in living systems. The parallels drawn between cosmic and biological evolution highlight common themes of gradual change through incremental processes, the role of randomness, self-organization, and the interconnectedness of components. By exploring these similarities, we can gain a deeper understanding of the underlying principles that govern both the universe and life, which will facilitate an interdisciplinary dialogue between cosmology and biology. Linguistic structures play an important role in shaping our ability to discuss and theorize about complex concepts such as nothingness and the early universe. How we formulate language not only reflects our thoughts, but also influences how we formulate ideas and communicate abstract concepts. This relationship between language and thought can have a profound impact on our understanding of fundamental cosmological ideas. One of the most important aspects is how the language we use can limit or facilitate our conceptualization of nothingness. In many languages, the term nothing is loaded with meanings that may limit our ability to fully understand the idea of total absence. For example, the use of negative constructions in sentences often relies on binary oppositions such as something and nothing, which can inadvertently anchor our thinking to a more dualistic understanding of existence. As a result, discussing nothingness becomes challenging because our cognitive frameworks are often not designed to readily accept the absence of concepts. This limitation can affect philosophical and scientific discussions about the nature of the early universe, where ideas about the vacuum or conditions before the Big Bang are framed within existing linguistic structures. In addition, the vocabulary available for discussing abstract concepts greatly affects the complexity of the ideas that can be communicated. For example, rich terminology in physics and cosmology allows scientists to expound subtle theories about the origin of the universe, while the absence of such terminology can impede progress. Developing a precise language to describe phenomena such as quantum fluctuations or singularities may increase our collective ability to grasp these ideas, stimulating further study of the early universe. Theoretical insights may be related to how effectively such concepts are communicated through language. In addition, linguistic structures can shape cultural views on concepts such as nothingness. Different languages and cultures may have unique approaches to discussing the void or conditions that existed before the creation of the world. These culturally fixed linguistic frameworks can influence societal perceptions of cosmological principles and even dictate the philosophical implications associated with non-existence. Such cultural perspectives play a role in guiding scientific research and encouraging some interpretations over others. Moreover, cognitive linguistics argues that the way we construct sentences can influence our thought processes. For example, languages that use metaphors, analogies, or spatial representations can influence how people formulate their understanding of abstract ideas. If a language encourages a narrative or framework that allows for flexibility in how the universe originated, it may lead to more innovative theorizing. Conversely, rigid linguistic structures can inhibit new approaches to discussing fundamental cosmic concepts. Linguistic structures significantly influence our ability to discuss and theorize about nothingness and the early universe. The limitations and richness of our language can shape conceptualization, guide scientific discourse, and reflect cultural perspectives. By recognizing the relationship between language and thought, we can strive to develop better ways of formulating abstract ideas, which will ultimately improve our understanding of the fundamental nature of being and the cosmos. Complexity theory provides valuable insights into the origin of the universe by exploring how simple components can interact to give rise to complex and emergent systems. This view emphasizes that the universe is not simply a collection of isolated elements, but rather a dynamic network. Complex structures emerge over time as a result of interrelationships and interactions. One of the key points of complexity theory is the concept of emergence, which describes how new properties or patterns emerge from the interaction of simpler elements. In the early universe, fundamental particles such as quarks and electrons interacted according to the laws of physics, leading to the formation of atoms and later stars and galaxies. By viewing the universe through the lens of emergentism, we can better appreciate how simple initial conditions shaped by physical laws evolved into the rich tapestry of structure we observe today. This view challenges reductionist approaches that seek to explain the universe solely by examining its individual components. In addition, complexity theory emphasizes the importance of feedback loops and nonlinear dynamics in the evolution of systems. The expansion of the universe after the Big Bang and the interactions between cosmic structures can be viewed as complex systems that exhibit nonlinear behavior, where small changes in initial conditions can lead to very different outcomes. This concept parallels the ideas of chaotic systems, where predictability can be lost over time. Understanding these dynamics allows researchers to build more accurate models of cosmic evolution, covering everything from the formation of galaxies to the distribution of dark matter. In addition, complexity theory encourages interdisciplinary approaches to the study of the origin of the universe by incorporating aspects of sociology, biology, and computer science. This broad perspective can foster innovative methodologies to provide new insights into how complex cosmic phenomena operate. For example, models originally developed in fields such as ecology or network theory, where the principles of interconnected systems are similarly applicable, can be used to study the formation of large-scale structures in the universe. Another intriguing aspect of complexity theory is its emphasis on the adaptability and resilience of systems. The universe has gone through various stages of evolution, from the formation of the first atoms after the Big Bang to the emergence of stars and galaxies. Adaptability is manifested in the way structures persist and evolve despite changing conditions and cosmic events. Recognizing these features in cosmic evolution may improve our understanding of how resilience arises in biological systems, leading to a more complex view of nature. Complexity theory offers a deep understanding of the origin of the universe, emphasizing the role of emergence, nonlinear dynamics, interconnections, and adaptability. By applying these principles, scientists can further understand how the universe evolved from simple initial conditions to the complex and intricate cosmos we observe today, fostering interdisciplinary approaches that expand our understanding of both cosmic and biological phenomena. Computer science concepts, particularly information theory, have intriguing applications in the field of pre-Big Bang physics, providing a framework for exploring the nature of information, entropy, and the underlying order of the cosmos. These principles can enrich our understanding of the early universe and the conditions that may have existed before the Big Bang. One of the central applications of information theory in this context is the concept of entropy. In information theory, entropy measures the amount of uncertainty or information contained in a system. Similarly, in cosmology, entropy is a critical factor in understanding the state of the early universe. Before the Big Bang, the universe is believed to have been in a state of high homogeneity or low entropy, where matter and energy were uniformly distributed. Understanding how information and entropy are related can help physicists study how small fluctuations in this homogeneous state could have produced the structures we observe today, including galaxies and cosmic filaments. In addition, information theory emphasizes the importance of data transmission and storage, which can serve as an analogy for understanding processes in the early universe. Just as information can be encoded and transmitted in different systems, so fundamental physical processes in the pre-Big Bang era may have involved encoding energy and matter in ways that laid the foundation for the evolution of the universe. Exploring these ideas within the framework of information theory allows researchers to think critically about how energy and information were interconnected at this primordial stage, leading to discussions about the fundamental nature of reality itself. In addition, concepts such as the holographic principle, which suggests that all the information of the universe can be encoded on a lower dimensional boundary, may overlap with ideas from computer science. This principle implies a profound relationship between information and the physical structure of the universe. If the information content of the universe is fundamentally related to its geometry, then computer science's knowledge of data compression and encoding can be valuable tools for understanding how complexity emerges from simpler components in a cosmological context. In addition, in recent studies of quantum mechanics, scientists have identified interesting connections between quantum information theory and cosmology. Studying quantum entanglement, superposition, and particle behavior at a fundamental level can spark ideas about how information is processed in the fabric of the universe. This leads to questions about what role information may have played in the transition from the pre-Big Bang state to a more complex universe. Information theory provides powerful concepts that are applicable to pre-Big Bang physics, illuminating the relationships between entropy, data encoding, and the fundamental nature of the universe. Using insights from computer science, physicists will be able to further explore the complex relationships between energy, matter, and information, ultimately deepening our understanding of conditions that existed before the cosmos as we know it. Sociology offers a valuable perspective on how scientific communities develop and accept theories of the early universe, emphasizing the social dynamics, cultural influences, and collaborative processes that shape scientific knowledge. Understanding these sociological factors can shed light on how theories develop, gain momentum, or face resistance in the scientific community. One of the most important aspects is the role of social networks and collaboration in the development of scientific theories. Scientific discoveries often occur through the collaborative efforts of researchers from different disciplines. In the field of cosmology, The exchange of ideas and data between scientists can foster a more inclusive environment where different perspectives are considered, allowing for a richer discussion around theories of the early universe. Sociologists explore how these networks facilitate communication, allowing researchers to build on each other's work, leading to the refinement and evolution of theories over time. In addition, the process of reaching scientific consensus is shaped by sociological factors. Acceptance of new theories often requires validation and endorsement by respected experts and institutions in the scientific community. The need for peer review can lead to the phenomenon of scientific scrutiny, where some theories gain prominence while others are sidelined based on the social status or authority of their proponents. Sociological research can help reveal how power dynamics and authority influence the prioritization of theories, shedding light on the mechanisms by which scientific communities reach consensus around complex ideas about the early universe. Cultural context also plays an important role in the formation and reception of theories. Scientific progress is not isolated from cultural beliefs and societal values, which can shape research priorities and influence funding decisions. In the case of theories about the early universe, broader public interest in understanding the origin of the cosmos can stimulate funding and media attention, creating the conditions in which specific theories become prominent. Understanding this interaction between culture and science can provide insight into how societal narratives can influence the acceptance of certain cosmological models. In addition, sociology emphasizes the importance of public and educational involvement in the development of scientific theories. The ways in which scientific ideas are communicated to the public can have a profound impact on their acceptance. Engaging the public through accessible accounts of the early universe can foster interest and understanding, which in turn can influence how scientific communities perceive the relevance of certain theories. Positive public attitudes can lead to increased funding and support for these areas of research, influencing which theories are further explored and accepted. Finally, the study of scientific revolutions proposed by sociologist and historian Thomas Kuhn shows how paradigm shifts can lead to the adoption of new theories. When existing concepts are confronted with anomalies they cannot explain, such as new observations related to the early universe, scientific communities may experience crises that prompt a re-evaluation of established ideas. Sociological analysis of historical shifts in thinking can help identify factors contributing to paradigm shifts, providing a context for understanding how today's theories may evolve in response to future discoveries. Sociology makes a significant contribution to understanding how scientific communities develop and accept theories of the early universe. By examining the role of collaboration, consensus building, cultural context, public engagement, and paradigm shifts, we can further understand the social dynamics in scientific inquiry and how they ultimately shape our understanding of the cosmos. Economic models of resource allocation offer intriguing parallels to the distribution of matter and energy in the early universe, emphasizing that both systems can be understood through principles of distribution, scarcity, growth dynamics, and evolution. By studying the similarities between these processes, we can understand how the universe evolved from a homogeneous state to the complex structures observed today. One of the fundamental concepts of economic models is the distribution of finite resources, which is directly related to the distribution of matter and energy in the early universe. Shortly after the Big Bang, the universe was characterized by a nearly uniform distribution of energy and matter. As the universe expanded and cooled, quantum fluctuations created fluctuations that led to localization of the density of matter. Similarly, in economic systems, the distribution of limited resources can lead to inequalities and differences in access. The way these resources are distributed may parallel how gravitational forces in the universe gather matter to form galaxies, stars, and planets, reflecting a denser distribution of resources within a larger structure that is expanding. In addition, concepts such as market dynamics and competition can serve as valuable analogies to cosmic processes. In economics, competition between agents drives innovation and efficiency improvements, which can be compared to the competition between gravitational forces that determine the formation of structures in the universe. For example, areas with higher concentrations of matter can attract more mass, leading to the creation of complex systems such as galaxies. This competitive aspect parallels market forces in economies, where actors seek to optimize their positions in resource allocation, leading to unequal but sometimes beneficial outcomes in the context of growth and stability. Another concept common to these fields is the feedback process. Economic models often illustrate how feedbacks between resources, such as reinvestment or depletion of resources, can affect their future availability and distribution. In cosmology, the dynamics of matter and energy also exhibit feedback mechanisms. For example, the accumulation of matter in galaxies can increase gravitational attraction, attracting more matter and promoting further growth. Understanding these feedback loops, whether in an economic context or in cosmic evolution, helps illustrate how small changes can lead to significant, sometimes unpredictable outcomes over time. Moreover, the study of entropy and thermodynamics, which are often used in economic models to analyze resource allocation and scarcity, has parallels with cosmological processes. In economics, the second law of thermodynamics can help explain how systems evolve toward equilibrium. In the early universe, as it expanded, the distribution of energy and matter increased entropy. As structures form as a result of gravitational clustering, the energy states of the universe change, leading to a more organized distribution of matter, just as economies move from a state of scarcity to a state of organization and stability. Economic models of resource allocation are related to the distribution of matter and energy in the early universe through the concepts of distribution, competition, feedback mechanisms, and the evolution of systems over time. By recognizing these parallels, we can deepen our understanding of both economic systems and cosmic evolution by highlighting how complex interactions can give rise to rich structures and dynamics in seemingly disparate domains. Music theory offers a fascinating look at the concepts of harmony and symmetry in the cosmos, revealing deeper connections between art and science. The principles of music, especially those related to harmony, rhythms, and structures, can serve as an analogy for understanding the interrelationships and patterns in the universe, improving our understanding of cosmic phenomena. One key area where music theory intersects with cosmology is the concept of harmony. In music, harmony refers to the combination of different tones or tones that create a pleasing sound or balance. Similarly, the universe exhibits harmonious relationships through the interplay of fundamental forces and particles. For example, the fundamental forces of nature, such as gravity, electromagnetism, and nuclear forces, can be viewed as a symphony of interactions that govern the behavior of matter and energy. Just as harmony in music is achieved through the careful arrangement of notes, the balance between these forces creates the complex structure and behavior of the universe, leading to the formation of galaxies, stars, and even the conditions for life. In addition, symmetry plays an important role in both music and the cosmos. In music, symmetry can be observed through patterns and repetition in melodies and harmonies, creating a sense of balance and coherence. In astronomy and physics, symmetry is a guiding principle that helps describe the laws of nature. For example, conservation laws in physics, such as conservation of momentum and energy, are often based on symmetric properties. In particle physics, the symmetries associated with fundamental particles dictate their interactions and behavior at the quantum level. Understanding how these symmetries manifest in the cosmos can provide insight into the fundamental structure of the universe itself, just as symmetry creates structure and form in musical compositions. Another area in which music theory provides insight is the use of scales and intervals. Musical scales, consisting of specific intervals between notes, set the framework for creating melodies and harmonies. Similarly, the relationships between different physical quantities in the universe, such as time, space, and energy, can be viewed as a kind of scale. For example, the concepts of redshift and blueshift of light from distant galaxies can be compared to musical intervals that convey motion and change. This analogy emphasizes the interplay between frequency and energy in sound and light, enhancing our understanding of phenomena such as gravitational waves and cosmic expansion. Furthermore, the use of rhythm in music can be correlated to the cyclical patterns observed in cosmic phenomena. Celestial bodies, such as planets and stars, exhibit rhythmic behavior in their orbits, often reflecting predictable patterns due to gravitational interaction. This cyclical behavior can be compared to rhythmic patterns in music, where beats and measures create a sense of order and predictability. Recognizing these rhythmic patterns in the universe helps us understand complex systems and the dynamics that govern them. Insights from music theory concerning harmony, symmetry, gamma, and rhythm can deepen our understanding of the cosmos. By drawing parallels between the structured beauty of music and the complex order of the universe, we can appreciate the underlying principles that govern both realms, enriching our perception of existence and the relationships that bind us to the cosmos.